Okay, we've got this function. It's just like drawing a direction field and differential equations, but with a slightly different uh, application. So we got this square here. This is 1, 1. I say this is a square centered at the origin, so we know what the coordinates at other points are. If x and y are both 1, then what's f of x, y? Well, that's I minus j, right? Okay. So what's I? Well, I would be here. And negative j would be here, so it would be like so. So here I've got a little I, here I've got a little j, and right there is my vector. Now, some of you got the vectors backwards in places and stuff like that, but most of them had, had the right idea. Okay, whether you got the details right or not, well, just be more careful. What about here? Well, that's 0, 1. X is 0, y is 1. Okay. Yep. It's actually up like this, and that doesn't seem right to me. But never mind, it's up with 1, 0. That's using 0, 1. That's right. F of 1, 0, x is 1, so you're going to get a negative j, y is 0, so you're not going to get an I. Okay. Now, when you draw the rest of these, now let's just do F of 1, negative 1. Okay, x is 1, so you're going to have a negative j, and y is negative 1, so you're also going to have a negative I, so that's going to be here. And if you're just careful putting the numbers in, that's what you're going to get. Well, this pattern is going to continue around here, and like so, and like so, like so, and like so. Okay, that makes sense. So if you go around here, the vectors always have a component. Okay, well, let's say you go around clockwise, counterclockwise, which is a positive direction. Okay, if you go around this square in the positive direction, the component of your vector field is always in the direction opposite to your direction of motion, right? Okay, so if I'm moving up here, I get to here. Okay, well, here's my direction of motion. Here's my vector. So my direction of motion is up here. The component of my vector in my direction of motion is this. It's negative, right? That makes sense? You want to be able to visualize that. So everywhere here, if this is a flow, okay, let's just say this is a fluid flow. Okay, what's that fluid doing? Okay, well, I immediately got the word vortex. Okay, yeah, it's circulating, fluid circulating, sorry, like this, in the clockwise direction, which is the negative direction for rotation. Right-hand rule tells you then that this circulation is in that direction. Okay, you can't say that it has a direction in the plane because the direction in the plane is always changing, but it does have a single direction perpendicular to the plane. Okay, that's the first thing I want you to see. This is a circulating field. And it's symmetric with respect to the origin. In other words, what you have here is equal and opposite to what you have here. So you take a point and reflect it through the origin, get the opposite direction with the same magnitude, okay? And that's true of any point along here. Now you can flesh it out a little more. You see that the field is going to go from here to here. It's going to go continuously. It's probably going to be, well, the angle with the vertical direction is probably going to, the angle is going to tend toward the vertical direction. This will come down here. And we come down here, then it's going to come out a little bit. It's down here. So you could flesh this out. But you basically, just with the points that I asked you to draw, you don't even need the points here. Although if you did the points here, they'd be half as long as the points we have there. And it's worth kind of sketching that. Understand a little bit more about this vector function, okay? So it's circulating faster out here than it is in here. Now, that ain't the way a vortex works. Okay, vortex, you probably have a faster circulation here than you have here. Okay, so it's not strictly a vortex. It's not even strictly something that would be that easy to achieve. Okay, with a fluid, maybe with a gas, but less so with a liquid. Not just speculating. I haven't thought it through. Question, hang on. Excellent suggestion. I've got liquid in here. If I just start spinning this around, what happens? Maybe I do get greater velocity here than here, right? So that was very good. Okay, so yeah, you can get that. Something like that. And there are probably other ways. So spend a lot of time looking at creeks flowing down the mountainside. See a lot of this stuff. Okay. Anyhow, very good. So I was thinking maybe more of a drain here because of the vortex thing, and my mind didn't extend to this. And somebody got that very quickly. Very good. Okay, circulation about the organ. Anyway. Okay. If I was to draw the same field on the unit circle, what do you think it would look like? Go ahead and sketch it. Okay, most people do something like this. Intuitively, you might expect that these things would all be tangent to the circle. Just the geometry kind of compels it. It's turned out it's true. It's very easy to prove that. Okay. So why is it tangent to the circle? Easiest way to prove that, I think, is to prove this always perpendicular to a radial line. your radial line. In the direction of x, y plus y, say. So f of x, y is always perpendicular to the radial line. Now, since that dot product is always zero, of course, the dot product, you dot this with this, you're going to get xy minus xy, right? It's always going to be zero. So I'm not going to, work out the details of that. They're obvious. Also, if x is y, x, y is on the inner circuit, we know that the square root of x squared plus y squared equals 1. Also, we know that the magnitude of f of xy equals magnitude of yi minus xj equals square root of yi minus xj dot itself. I'm not sure how much that I want to write out. I kind of do want to write it out, so I'll squeeze it in. Equals and that comes out square root of y squared plus x squared of x squared plus y squared. So with this simple function, we can probe a lot of the mysteries of the world. Okay. And we can also kind of review some of the stuff we need to understand, some of the techniques that come through from what we've done so far. Make sense? Okay, I'll give you a couple more examples, simple ones, but they show, well, really trying to give you a preview of the whole chapter 15. Okay, whole chapter in vector calculus, which is really the point of this course. So we're doing the same thing we did before, but with this function. Okay, so make kind of sloppy square and a sloppy circle. But if we have 1, 1, then we're going to get I plus j. If we have the point 1, 0, we just have I. If we have the point 1, -1. Then we have 1 this way, -1 this way, so that'd be 5 minus 1. And if you continue around here, it's going to look like this. Now, I haven't been very careful about the lengths of my vectors, but I plus j is about 40% longer than just I or j by itself, right? Hypotenuse is 1 by 1 triangles, square root of 2 about 1.4 in length. So it's a little longer here, 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 and here than it is in the in-between points. So I can kind of special exaggerate this one a little bit. And maybe they look a little bit longer up there. You get the idea. Now, if you do this on the unit circle, it's going to be same here, 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 and here, as opposed to here, 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 and here, because they're the same points. If I go up to this point, well, x and y are equal, let's say I'm at 45 degrees, so that the I and j components will be equal, they'll both be positive. Something like so. And down here, same thing. And here the same thing. And here the same thing. Okay. So what am I looking at there? How would you describe this vector field? Okay, the word I immediately got was repulsive. Oh, I think it's kind of cute. It's like you got a charge here and everything's being repelled, or explosive. Yeah, we got something explodes here and everything diverges, right? Okay. Well, now the word I would say here, I mean, I like the words you use. They're beautifully descriptive, but the word we're going to use is have a diverging field. Okay. And this is a circulating field. Okay, well, yeah, let's get a picture of it here. The picture over there is off of the camera's range. Okay. Well, I'm going to give you just a couple little previews because I want to get you thinking about the concepts that are central in this chapter. What's del dot G? Find out what you think del dot G would be. And this, that's what it is. You don't skip the definition just to get the answer. Okay. So it's just a little advice. I mean, I understand I did the same stuff, but well, not in this course, I had plenty of time to do it, but if you're writing things out completely, you don't skip the step of writing out del. It only takes 3 seconds. Okay. And if you skip the step of writing out del, then you don't know what del is. You just know that del f is fxi plus fyj. Okay. You skipped the definition. So now that when you need the definition to answer a simple question, you ain't got it. Okay. So just recommending you write out details because that's how you learn. Okay. That's how you retain them. If you got other ways of retaining them, everybody's mind works differently. But make sure you're learning stuff. You're doing stuff in a way that reinforces as much learning as possible. Because while you're in a situation, that's the most efficient time. Take just a little extra time to enhance what you're, okay, well, so that makes sense. Okay, so now what would del dot G be? See if you can figure out what del dot G would be. Write out del dot G equals, and then write del and write G with a dot in between them, and then see if something obvious comes out of it. Okay. First of all, hey, what's G? Right there. Okay, so. Okay. Now you dot this with this. It means you're going to multiply. That's not actually multiplication. This is not a vector, it's a vector operator, but it acts just like it was a vector, except it's not. Okay, and by that I mean, it's like you do the partial with respect to x times the x, except it's not a multiplication, it's an operation. Okay, and that's what, yeah, some of you did. It's partial with respect to x of x plus partial with respect to y of y, which equals 1 plus 1 equals 2. Now, if you want to write it out the way you did, you could say, okay, it's partial with respect to x, comma, partial with respect to y, dot x, y. And if you wrote it out like this, it'd be okay. But to put fx, fy here wasn't a good idea. Understand why that might be a little confusing and mislead you. So you should understand either notation, be able to use either notation equally efficiently. Okay. But you're going to see different authors write it differently. So be aware of the two main notations. Okay. Oh, that's good. How about del cross G? Okay, first of all, del cross G is there's a distributive law. This means partial with respect to x of x times I cross I. Because you do this times this, or you combine this with this, you're going to have an I cross I. Of course, I cross I is 0. Then it's partial with respect to x of y times I cross j. Then it's partial with respect to y of x times j cross I plus partial with respect to y of y times j cross J. Well, I cross I is 0, J cross J is 0. And the partial with respect to x of y is 0. Okay. So we have 0, I cross J is K. Plus, then plus 0 times negative K, which of course is just 0 K. Right? Now that's using the distributive law. And if you write it down in the determinant, as you probably will, there's your determinant. You're going to have I times the partial respect to y of 0, which is 0, minus I times the partial respect to z of y, which is 0. Okay? Everything comes out 0, one way or the other. Your partial with respect to x of y, your partial with respect to x is 0. Partial with respect to x of 0 is of course 0. Partial with respect to z of x is 0. They're all 0. Okay? That's just the 0 value. Okay. Now let's see what that tells you about these vector fields. Del cross G is 0. Okay. This is because the del cross operator is a test of circulation. Is there any circulation here? It's not circulating. It's divergent. Okay. The del dot G is a test of divergence. Okay. You do del dot G, right there's your G function. It's diverging, and you get 2. Okay. Which is the maximum you could get from a vector of magnitude 2, turns out. Okay. So you have a test for the amount of divergence, and you have a test for the amount of circulation. This vector field is diverging, it's not circulating. Okay. Well, let's see what happens if you do del dot F and del cross F. Okay. So what we get is del dot F equals 0. Del dot G is negative 2K. Right. So what's this telling us? Well, what this tells us, first of all, the del dot G equals negative 2K, which is interesting. Okay. Which direction of circulation? It's clockwise. Right hand rule tells you that's in the negative K direction, doesn't it? Circulation is in the negative K direction and has magnitude negative 2. I mean magnitude 2 in the negative K direction. Okay. You got 2 units of circulation. Okay. And the circulation is in the negative k direction, meaning you have a circulation in the plane that's clockwise rather than counterclockwise. If it had been negative xi minus yj, your circulation would have been in this direction. Okay. So what did Del tell us? Well, del dot F was wait a minute. It wasn't G, that was L. Okay. I got two lines down there. Yep, yep. Again, it should have been del dot L, but that's what everybody did. And everybody either got 2K or about 2 steps short of getting 2K. Right? So your del dot L is this brush step. Okay, so del dot F is 0 means no divergence. Okay. And this says circulation is counterclockwise in the XY plane. Okay, I want to use besides F, G, I want to use H. I'm just going to say del dot is your divergence tester. I've used F and G for specific functions, so I'll use H. Del cross is your circulation tester. Now we don't use circulation, we use the word curl. The curl is a measure of circulation. Your book has a nice explanation of that. Okay. Maybe the best one I've seen. So I didn't get a very good explanation when I took this course. I didn't totally understand. I knew curl had something to do with circulation. We'd have done a simple example like this. I would have understood. But I wasn't quite smart enough then to make up simple examples. Okay. Now, these are things that aren't introduced until about 2 weeks from now, but they're simple operations and they give you meaning to these vector fields. Okay. And these are big deals. So I want you to start with an intuitive grasp of divergence and curl. Now we can do divergence of a function like xy plus y over x squared, something like that. It'll have non-zero divergence and non-zero curl. Okay. Meaning that there's some tendency to circulate. And at different points of the field, there'll be different points. You know, you have vortex here, you can have an explosion here, all kinds of things can happen. With more complicated functions. We don't need to get into complicated functions, especially since these calculations that we're doing. Now, these pictures are exactly what you're going to be asked to do for homework. Okay. And homework we do, I think, Monday. Just to give you time then to clear your brain and get ready for the test. I think you'll find it a very easy assignment because you've already done direction fields and you showed me you know how to do direction fields, okay? And it's just equivalent to doing direction fields. But there's, you know, you didn't do divergences and curls with vector fields. So I want to get you off the good start here. Okay. If we did path interval of this vector field around this circle, what would the result be? Well, think of a typical increment. What's the direction of your tangent line? What's the direction of your vector field? Okay. So, okay, what I want to do is talk about here what would be for this field in integral. It says integral f dot t ds, where ds is just your arc length parameter or whatever you want to use, and that's something you want to be thinking about. You've got a test coming up. Okay, I'll involve that. Okay, so just take your sketch of that picture or draw another one real quick and show me a typical increment and show me your tangent vector, unit tangent vector, and your vector function F vector. Okay. Okay, we're talking just conceptually about the integral of g dot t ds or f dot t ds. Okay, whichever function you want to do, whichever function you want to start with. You want to do both of them. Okay, well, here's your circle, right? And let's do that. Okay. So there's a picture represents that vector field on this circle. Now I want an increment of the circle. Now you've done arc length intervals and stuff. You probably want to review and see what's really going on with arc length intervals. If you're doing it by memorizing a formula, okay. But you really go a little deeper than that because you want to understand line intervals and not too long from now, surface intervals, which are pretty tricky. You want to get a good understanding of that. You also want to understand that because you're going to be testing. Okay, try to get a deeper understanding of at least arc length intervals. Okay, and anything else about integrals along the curve. Now, your curve is the circle. An increment of the circle is, well, there's a good increment. Okay, just a typical increment. Can't read the whole word increment. I didn't write the whole word. But there's a typical increment of your path. So on that increment, you have a tangent line. Now, depending on how you set up your path, could be clockwise, could be counterclockwise. I didn't specify, did I? Okay. But let's assume we're going in the positive direction. Now I'm going to go in the negative direction to see if we can draw the arrow. So right here is my unit tangent vector. If you don't instantly understand that, you really want to go back to your tangent normal vectors and components and stuff like that, which someone did fairly well in the earlier test. But you really want to deepen your understanding because of what's coming. And it's a big deal. Okay, so anyhow, there's your unit tangent vector. And of course, here is the vector. Well, I should make this shorter because it's just the rest of it. There's your view vector. Okay. So you're going to do a sum of G dot T delta S. Okay, what can you tell me about G dot T? Okay, so somebody said, well, it looks like it ought to be zero. Because these things look like they're perpendicular. Now, really, in a typical increment, you can have any sample point in here. Okay. But whatever sample point you do, this G function is radial. And the tangent to the circle is always perpendicular to the radius. Okay. So it doesn't matter what your sample points are. And that's, okay, I'll put a little circle around here. That's a closed, the little circle here means you go all the way around the path. You end up where you started. Okay, means a closed path. And you experience that back when you look at conservative functions. It's fine here, that's right. I think, actually, it might be coming up, I don't know. Yeah, I think actually the way to this chapter to do conservative. Anyhow, that's what it means. So I'm going to put a little circle here. Okay, well, what about the G function? What about the F function? Well, here's your F function. It's like this, a typical increment. And incidentally, when you do the typical increment, don't put it on the x-axis, don't put it on the y-axis. You want an arbitrary point, and a point on the x or y-axis is likely to have unique characteristics that aren't going to generally be so on the curve, okay? So you pick something that isn't a particularly special point. So I'll go out here. Okay, so here's my typical length. On this typical increment, here's my G function. So I'm going to kind of erase that one so it doesn't overlap. But here's G. Where's my tangent line? Well, assume a clockwise path so that your unit tangent vector isn't right on top of the G vector. So here's your unit tangent vector. So on this interval, G is tangent, unit tangent vector is tangent. Okay? G dot T equals then the negative magnitude of G times magnitude of T. So the sum of G dot T ds equals the sum of the magnitude of G times the magnitude of T ds. The magnitude of G as defined is square root of 2 . Well, actually, we'll just do the square root of x squared plus y squared, but on the unit circle, it would be the square root of 2, right? And actually, no, it's that times the magnitude of the unit tangent vector, sum, times ds. Now, I haven't stated that this is a unit circle, although it was before. Let's state it so we can assume this is a unit circle. On the unit circle, square root of x squared plus y squared is always 1. It's the sum of your ds's. Your ds's or your delta s's are the lengths of these increments, and you go all the way around a circle of radius 1. You've done the circumference, right? And that's 2 pi not pi. Oh, I thought it was pi. Okay, 2 pi, right? So you don't have to do any integration at this point, but this is what the integrals mean. And if the function is not nice, like this one, where G is always perpendicular to T, or this one, where G is always parallel to T, then you have a mixture. Now, if G is always perpendicular to T on a circle about the origin, that means that this thing has no circulation. It's divergent. Okay. Here, no divergence. It's circular. Again, these integrals provide you with a similar test. And I use G throughout here when the function is out. So you don't have to stick around and watch me fix it. But I'll make sure it helps. Move the next one. If you digest everything I've told you today, you're off to a good start in this very tough chapter. Okay.